So if we take a look, today we're going to discuss polarity and some more of those exceptions that we've been talking about. And then we have the laboratory for tomorrow. So if you click on that, there's the requirements for the laboratory. You'll be able to work in groups of, how big is this class? Let's see, we got 13 people. So I have enough for 7 groups. So looks like groups of 2 maybe. If you're absent on day 1, you can do it all by yourself. So if you're absent tomorrow, you'll need to get it done by yourself. The atoms in your compounds must be roughly the correct size. We said you can cut pieces of the dots off and stuff like that, or you can use color to show the differences. I'm sure that you'll be able to realize that, you know, a carbon is going to be bigger than a hydrogen by 1 valence shell. Lone pairs on the central atom must be represented. We said you could do that with a marker. The molecule must have the correct shape. Now that's the biggest part right there. That's why we're doing this. And again, we're doing this without, you know, pre-drilled holes and stuff, so that you actually have to form the shape. That's the idea behind it, so that you actually have to form the shape. A lot of times when I do this, I get a lot of stuff that just lays directly flat on the table. You can remember that these are not flat laying on the table shapes. These are 3-dimensional things. Non-perishable. Since all you're giving me is pictures, I don't care if you use something that's perishable. Each of the molecules should have its own picture, and it should be ordered by the top to the bottom of the key. I'll show you the key in just a second. Resonance hybrids must be drawn, but they don't need to, you don't need to make one, you can just make one model for all of them, and then the key. So if we pick group 3 or group 1 here, each group has their own 6. So this is group 1's 6 different molecules they need to make. You draw the Lewis structure in this box. You give the geometry and the angles in this box. You tell whether it's polar or non-polar in this box, and then you build the actual model. Easy enough. So that means that you would attach to this file 6 pictures of the different models, and they would order by carbon monoxide, and then this nitrate ion and the sulfite ion, nitrite ion and the sulfite ion. So that's
Mr. Jack.
Big goal for this unit is to be able to build these. Yeah, question.
So should we just submit pictures by like our phone, or is there any other better way you want it with the models?
Yeah. The best way, unfortunately, is probably with your phone. That'll be the easiest for most of you. Yep.
And then also for the lone pairs on our models, can we use like smaller like toothpicks? Like
yeah, sometimes people like cut the heads off of gummy bears, like some demented, you know, gummy bear killer, and then they use like the head of the gummy bear for the lone pair. Yep.
Okay, cool. Thank you.
Yep. The key thing on this is that your model is 3 dimensions. If you're sitting there looking at it and it's all flat, that's something that's planar. So unless it's trigonal planar, then that's not going to work, right? So keep that in mind. All right.
Mr. Jackson.
Yeah.
Are we choosing our groups, or are you choosing for us?
To tell you the truth, I don't care.
Okay.
Yeah, so if you have a group in mind or whatever, I'll let you do that. Yep. Do we have a go-to for a group of 3 since we have an uneven number? Oh no, we got 16. Okay. Well, there will be 2 groups of 3 then, right? So I'll let you guys think about that. We'll talk about it tomorrow. Basically what I'll do is I'll put you in Zoom rooms or whatever they're called, breakout rooms, and then basically, you know, do it that way. All right. So if we take a look, that is, yeah, question.
So do we only turn in the ones that we did, or do we turn in all of, like, because some people will be doing different models, like we split them up?
Well, that's the thing. You turn in one key and all of your pictures.
Okay.
For your whole group. Yep, for your whole group. Yep.
Okay. Thank you.
Mm-hmm. And so we'll do that Wednesday and Thursday. We'll finish it up. See, like it says here, each group must turn in an answer sheet and picture for each molecule. Just one answer sheet and group a set of pictures. Okay. So today we want to talk about exceptions and polarity. I feel like we've gotten a lot of the exceptions done already. So I'm going to have this sheet right here ready for you to look at. Is this groups? This is period 4, 5, 6. All right, so here's period 7, 8, 9. A lot of these exceptions on page 18 we have already covered. It looks like. Let's do XeO3. Oh, and I need to show you the picture. Looks like. Visualizer. So if we take a look, XeO3, Xe is going in the center. 8 plus 18 equals 26. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Well, that's kind of boring. What's the shape here?
Trigonal pyramidal.
Good, trigonal pyramidal. Any more exciting ones on this side? Let's try this one. XeF2. Xe in the middle again. That's 8 plus 14, which equals 22. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. What shape do we have there?
Linear.
Linear. Good. Linear. So if we take a look, remember any extra electrons go on the central atom. So here I had 20 would have fulfilled the octet for everybody, but we had 22 electrons, so they go on the central atom to basically finish it up. SbCl6, 1. Antimony has 5. 6 times 5 is 30. So we have a total of 36 because we have the -1 here. It's a big glare there. There we go. So antimony goes in the middle. See,
Wait, Mr. Jackson.
Yeah.
Doesn't Cl have 7 valence electrons? So why would we take
What did I
5?
do? 5. I multiplied it by 5. Good call. 6 times 7 is 42. Plus 6 is 48.
Yeah.
Yeah. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. 6 bonded atoms and 0 unshared pairs. What do we got?
Octahedral.
Octahedral. Good. Oh, really knows. All right. 5 plus 7 times, that's 28. Minus 1, so it's going to be 32. Another boring one. What's the shape of this one going to be?
Tetrahedral.
Tetrahedral. So yeah, I mean, this, it's the same stuff we've been doing. We just have a little few more shapes this time. The only other big thing is if it's an acid, you know it's an acid because hydrogen is the first element. And when you have draw the skeletal structures for acids, H's are always attached to the O's. So if we take a look here, the P is going to be in the center there. And then we will attach H's. Two, 4, 6, 8, 10, 12, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. 8 plus 4 times 6 is 24 equals 32. What is the shape if we were to look at the P?
Tetrahedral.
Good. And what are the shapes if we were to look at the OH part?
Angular.
104.5. Yep. These will have the bent or angular. Yep. Others? Questions? Let's take a look at this one. We have SO3. Now that's where it gets tricky. We have H2SO3. You need to recognize that that hydrogen means this is an acid. So instead of putting the H off of the S, it has to come off of the O's. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 4 times 6 is 24, plus 2 is 26. What's the shape of this one? If we look at the S.
Trigonal pyramidal.
And the shape of the O's.
Angular.
Angular or bent again. Questions there? All right, you can finish these up for practice if you need it. I'll try to get the answers and then post them by tomorrow. Last thing we need to discuss today is polarity. Is it polar? Well, basically, we will look at what's called the electronegativity difference. So the difference between carbon and fluorine would be 1.5. Then you have this list right here. If it's 0.4 or below, it's nonpolar. If it's 0.5 to 1.9, it's polar. If it's greater than 2, it's ionic. So this would be polar. Now they show the bond here. The fluorine has a higher electronegativity, so the electrons that make up this bond are not shared evenly. They're going to be pulled closer to the fluorine. So this is like your uncle or that one cousin that, like, when they go to shake your hand, they try to pull you into them or whatever, right? They try to pull you off balance or whatever. That's what's going on here. The fluorine is pulling these electrons closer to it. Now, if it had the ability to pull them all the way off, then it would be ionic. So basically, this is equal share, unequal share, taking. So this is equal share of electrons, unequal share, and taking electrons. Remember, electronegativity is that attractive force to those electrons. So the higher the electronegativity, the more it's going to pull those electrons toward it. So if we take a look between B and H, the bond between B and H has an electronegativity difference of 0.1. Where does that fit in here?
Nonpolar covalent.
Non-polar covalent. Remember, covalent is just a term for that sharing of electrons. CC, any bond that's bonded to any atom that's bonded to itself, like a like atom, is going to be non-polar because the electronegativity difference is going to be 0. CH. 2.5 minus 2.1, well, that is barely nonpolar. ASS, oh, 2.0 and 2.5. So we have 0.5. This is barely polar. I take the difference and I put it into this and I check it. That's all I'm doing there. So what that means is that this bond right here, the AS to the S bond, the electrons are being pulled closer to the sulfur. And that could be a way to represent that pull, is we put like a little plus sign and then the arrow going to the direction that the electrons are being pulled in. Another way you might see this is that somebody might put a lowercase delta positive above that to show that it has a partial positive charge. Or over here, the sulfur has a partial negative charge. So if we take a look, SNF, what's the electronegativity difference for SNF?
2.2.
2.2. So that's looking at ionic. So what has happened there is that SN has basically lost that electron. So we don't leave this arrow here. We basically put the SN like that and the F like that. Because it's ionic, it has taken the electron. The fluorine has taken the electron from SN. So this is positive charge, negative charge versus partial positive and partial negative. Now, the last thing that you would do to look at this is something like O and H. Well, the electronegativity difference for that is 1.4. So that means that we're going to have a partial positive charge at the hydrogen and a partial negative charge at the oxygen, because the electrons are basically being pulled this way and this way. Overall, there is a pull up and towards the oxygen. Right? Well, what that does is if hydrogen is bonded to an oxygen, nitrogen, or fluorine, it creates kind of a pretty special situation. We call this hydrogen bonding. So we know that the next water molecule will also have a negative and 2 positive partial charges. But this partial positive charge here will be attracted by this oxygen from another water molecule. We call that hydrogen bonding. That polarity allows oxygen to hydrogen bond with each other, and that's what causes the surface tension. And why water beads up or forms droplets. Since there's an overall pull in one direction, we not only say that these bonds are polar, but the molecule itself is polar. So to determine if a molecule is polar, the first thing you have to do is know the structure. 6, 12, 18, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we're going to need to double bond. And this would actually show resonance. What is the shape of this? Hopefully you didn't fall for this on yesterday's quiz. While it may look linear, it's actually what?
Right?
Mm-hmm. It's bent. So what is the electronegativity difference between S and O?
One.
1. So these are polar. Where is the pull? Toward S or toward O?
Towards O.
Right? So if we have this looking linear, it might look like these two things cancel each other out, and it would thus then be nonpolar. Anytime you have two polar things cancel each other out, like a tug of war, it's nonpolar. But the fact that it is bent or angular, we can see better if we have it drawn like that, that these are not actually canceling each other out. While they may cancel out the left and right for each other, they don't cancel out the up and down. So if we take a look, this is pulling down and there's nothing pulling back up. So this would be not only polar bonds, but a polar molecule. If we take a look here at this methane or carbon tetrahydride, are these bonds polar?
No, they're nonpolar.
If it has only nonpolar bonds, then it cannot be a polar molecule. Let's see CF4. What's the electronegativity difference here?
One and a half.
1.5. So these are polar. But the difference here is that all of them are the same. What's the shape of it? Tetrahedral. If I pull this way and this way, these two are going to cancel out each other left and right. And since they're all the same, this one's going to cancel out, top and bottom, as well as this one. They're all going to be pulling in opposite directions. So even though the bonds are polar, it is a non-polar molecule. So if you imagine that the carbon is like a ring, and these bonds are like ropes attached to that ring, if all of these pulled at equal strength to each other, that ring would not move. Right?
So would that be the case in all tetrahedrals because of their shape?
Well, let's take a look. So now we have two F's and two H's. The shape again is tetrahedral. If we take a look, here we have this. Again, what did you say the difference was? 1.5? Yep. So if it pulls that way and that way, do they cancel each other out totally? If we had a ring right here and we pulled that ring in that direction, it would move because there's nothing pulling it back in this direction, right? So even though we have a polar bond here and a polar bond here, that's going to pull them out that way. Nothing's pulling them back. So that would be a polar molecule. So to answer your question, Emma, if all the bonds are to like elements, then yes, it would tetrahedral would always be nonpolar. But the fact that we don't have all like elements here, that allows us for variance. Let's say we just had one F, then that would be polar, right? Or if we had three Fs, then that would be polar. You need all of them to pull opposite directions. Questions? So let me ask you this. What's the difference, electronegativity difference for PCl?
.9.
So that's a polar bond, right? If you have something that's tetrahedral or bent and you have polar bonds, there's nothing pulling at that lone pair ever. So if you have polar bonds and you have a lone pair on the central atom, then it's going to be polar. Trigonal pyramidal. Right? Everything's pulling down. Nothing is pulling up to cancel that. So if it has polar bonds and it's trigonal pyramidal, it is polar, not polar, polar molecule. Go ahead and try the rest of those for this evening. Obviously, I don't need you to finish this side. That's just practice, you know. I mean, I'm hoping you guys can subtract things, but there's no need really for that one. Anybody have any questions before I let you go? Work on that. Oh, there's something in. Somebody is choosing to use the chat, even though I never read it. If you are absent, do you do one group of molecules by yourself or the molecules in each group? Just one group of 6. Yeah, that would be way overkill. Any other questions? Nope. Have a great day, guys. Take care.
Thank you. Have a good day.
Thank you.
Thank you.
Yep. Bye.
Have a good day.
I actually have a quick question.
Yeah, bro.
It's about so when there's a molecule with like 3 different elements, like what 2 elements do you choose to find the difference between their electronegativity?
So it's actually each bond. So if you're looking like at CHF,
Yeah.
you actually look at each bond individually. So here, you actually look at this bond, this bond, this bond, and this bond. Does that make sense?
Yeah. But the bond, so we said that bond was polar, but the bond between the carbon and the
Hydrogen.
hydrogen is non-polar.
Non-polar. Yep, that's true. So
How do
basically,
you fa-
it's a polar molecule because the bond between carbon and fluorine are polar, and they don't cancel each other out.
what do you mean cancel each other out? Like, is that just like
Like here, they all pull in opposite directions, so they're pulling those electrons all in opposite directions. They'll be able to cancel each other out, so that makes that non-polar. Here, they cannot cancel each other out because if you take a look, even though it looks like they could, one pulls left and one pulls right, in reality, they're pulling down and left, or down and right, or up and left, and up and right. So that even though they're pulling this way apart from each other, they're all pulling that way in that direction. Nothing is pulling back in that direction. So they don't cancel each other out.
is that somewhere in our notes? Just like a tab on it. Or we just get the note of that.
If the polar bonds cancel each other out, it will also be
Yeah.
not.
So like even like, so if there's like 3 of them, can they cancel each other out? And there's not a 4th bond.
It wouldn't happen because that lone pair of electrons can't pull any direction. So they would not cancel each other out because of that lone pair being on that top.
Oh. All right, that makes sense. That's all.
Yes, like octahedral can cancel each other out. Trigonal bipyramidal could cancel each other out. Tetrahedral could cancel each other out. Linear could cancel each other out. But the other ones with the bond on the central atom, they don't really have a chance to cancel out if the bonds are polar.
Okay. Well, thank you.
Hey, yep. Have a great day.
Too.